We're going to be doing a deep dive into source maps over the next few lectures. A source map basically takes some code which is being compiled and maps it back to the original source. This is primarily used for debugging. For example, you might have some ES5 JavaScript executing in your browser and you'd like to know which TypeScript maps to. What you can see here is a source map visualization application. You can see we have some source code compiled on the left to this ES6 or ES5 JavaScript, and the original TypeScript is over here on the right. You can see things like var is going to map to const, and then we have greet mapping to greet, and so on and so forth. And this is really useful for debugging. What we're going to do is build our own very similar app here, and there's a few things we need to do to make this a reality. We're going to be using no dependencies to make sure we learn as much as possible. You could of course just go and install a whole bunch of modules, but then you wouldn't really be learning anything. And my main goal here is to really expose how these tools work under the hood. So what we need to do first is take a look at the source map, figure out how to decode it, and then figure out how we can build this kind of data structure, and finally build a very simple web app using something like React or Vue to map out these things visually. So if we go ahead and head over to the terminal here, I have some source code to share with you. I have this original greet.ts file right here, and down the bottom I'm going to show you the compiled code. You can see they're very similar. Obviously we haven't got the type definitions that we have up here in the source code, and we also have this source code mapping URL down the bottom. The way I generated this was by running yarn tsc. I then passed in greet.ts, and then I passed in the source map flag, and it gave me this source map out of the box. If we have a look at the source map now, we can see it's down here. It is a JSON file which has some interesting information, like the original file or the compiled file is the greet.js, the original file is greet.ts, and down here is the really important part, the mappings. And you can see this big mess of jumbled characters, and this tells us how the compiled code maps back to the original code. Just to give you some perspective on how this actually works, because it's going to take us a while to get there, if we look at the very first mapping, AAAA, this is actually going to decode to 0000. The second one, IAAM, is going to decode to something like 4006. And I'm going to show you now how this is going to help us map everything up. Over here on the in my diagram, you can see how everything is mapping up. I've got the source code the original code down the bottom, and I have the compiled code up the top, and we have everything divided up into grids. Everything is 0 indexed as God intended it to be, so we start from 0, 0, and you can see this verse value here is saying 0, 0, 0, 0. The far value on the left is pointing to the column. In this case, it's going to be the very first column, and that's going to be referring to this V here. The last value here, the 0 on the right, we have it down here again as well. It's pointing to the original source code, and that's also going to be pointing to the very first column and row, C, and it's saying these two characters, the start of these tokens, match up. If we take a look at the next mapping, it's saying 4006, and what this is saying is in the compiled code, the fourth character is where the next token starts, and that's going to be this G in here. So now we can deduce the very first token is VAR and space. If we look at the last character here, it's going to be, or the last digit, it's going to be 6. That's mapping up to this G here. So we can see that VAR space var is going to map up to CONST space const. So now we can see how the original code became the compiled code, and this is very useful for debugging. And you can imagine how this continues working. We have many sets of these digits pointing to map everything up. These digits in the middle are about the row numbers. Obviously they're both 0 at the moment because we're on the first row, but as you go down you'll see those increasing as well. And this is kind of a direction we're going to be heading. The main focus of this lecture is going to be exactly what these digits are, or these characters are, and how we can decode them. And we're going to do this by looking at the actual source, or the standard for the source maps, which is over here in this Google Doc. Somewhat surprisingly, it's in a Google Doc, but this is the source that you have to look at when you're building something like this. And the reason it's in this Google Doc, as we can see up the top, is it was kind of invented by a bunch of guys at Google. If we scroll down a little bit, we can see some interesting information. And what we really need to look at here is this terminology to give us some clues. We've already seen the generated code. We know that's going to be the JavaScript. The original source, of course, is going to be the TypeScript code. And now we're looking at this definition, Base64 VLQ. And that is the exact encoding that is going to be used down here for these values. I'm just going to go ahead and close these off so we can actually get into a fresh buffer and actually show you how this stuff is going to work. So basically it's saying that these encodings are going to be Base64 VLQs. And if we read over this, we can get some more interesting information. We can see here it's saying the most significant bit, the 6th bit, is used as a continuation bit, and then we have a whole bunch of other information, but the main takeaway here is it's going to be 6-bit values. So these are also Base64 encoded. What you need to do is decode them, and then we can move forward from there. The way to decode something from Base64 is fairly straightforward. I have this Base64 table on the right. This is just a hard-coded kind of table you can grab from anywhere. We're going to create one in code later on, and this is going to tell you how you can decode things. So let's start off with a very simple example. I'm claiming that I is going to map to 4, and we're going to see how we can methodically do this based on that standard. So we start off with our value of I, and what we need to do is first decode this using the Base64 decoding. If we look over here in our table, we can see I is here, and it maps to 8, or in binary, it's going to be 0010000, and this is indeed going to be 6 bits. Of course, the first 2 bits are not very useful in this particular case. It's just going to be 1000, but it is important to recognize there's always going to be 6 bits here. The reason this is important, if we continue reading over here, is we can see the most significant bit, the 6th bit, is used as the continuation bit. The reason we have this continuation bit is because we only have 6 bits here, which means we can only represent a number, or at least a 5-bit number in this case, so the maximum value we can represent is going to be 11111, and this maps to 31. Of course, we're going to have numbers larger than 31, so what we do is have this continuation bit. If this first value here is going to be 1, that means we need to go ahead and grab the next packet and continue to use those as part of the original number. For example, in this case, YB, we know this is going to use a continuation bit, as we're going to see soon, so we actually use both of these characters to eventually come out with this 25 number in here. In the case of I, this is not the case. The most significant bit is going to be 0, which means there is no continuation bit. What this reflects is these remaining 5 bits contain all of the information required to decode this digit. So based on this, we can go ahead and delete this one here. We know this is not part of a number, it's just indicating there is no continuation bit, and we are left with these values here. The next thing we need to do is, if we continue reading, we can see that the digits are encoded in the string least significant bit first, where the least significant bit of the first digit is used as the sign bit. So what this is saying is the least significant digit indicates the sign, so if it's positive or negative. In this case, the least significant bit is right here, it's 0, and 0 means positive and 1 means negative. So this means it's going to be a positive number. This is not actually part of the number, it's actually just the sign value, so I'm going to delete this one now and place this plus sign here just to indicate this is going to be a positive value. And now we've finished doing all the decoding, this is our final value, and we can just go ahead and convert it back to decimal. This is fairly easy to do. I can just use parse int, we're going to pass it in here, so plus 0100, and we want it from base 2, and that value is 4, and that's exactly what I said. I is going to decode to 4. Now that we've seen this very simple example, let's go on and see a more complex one. We're going to look at J, and I'm claiming that J is going to decode to -4. So this is going to give us a chance to see how that the positive or negative signing works. So let's go ahead and start again. We are starting with J, and of course this is going to need to be decoded to base64 or from base64. Jumping over to our table, we can see J here. It is 9, which is going to be in binary 001001. So I'm just going to paste that one in here so we can keep track of it. The next thing we need to do is check if the most significant bit is a continuation bit. In this case, it is not, so we can just go ahead and delete it. The next thing we're going to do is check if the final bit is 1 or 0. In this case, it's 1, which means it's a negative number, so we can truncate that one and put the negative here to indicate that it's a negative number. And the last thing we need to do is go ahead and get our final value. In this case, it's going to be this value here. Let's jump down here and just double check that one now. We can see it is going to be -4, and that's exactly what I was expecting as well. So we've seen twice how this process works. We're now going to go on to our third and final example before we write some code, and that's going to be converting a more complex one, which is going to be YB in this particular case. The reason this is more complex is it uses a continuation bit. So let's go ahead and jump into this one. We are going to start off with Y, and if we come over to our base64 table, this is a lowercase y, which decodes to 50, which is going to be 110010. We're going to want to remember that one. While I'm here, I'm just going to grab the value for B as well, and that's going to be 00001, so we're just going to remember this as well. So if we observe this first one here, we can see the very first bit, 1, is going to be a continuation bit, which indicates these remaining 5 bits do not contain all of the information for this number. We need to use the next one as well. So with this in mind, I'm going to just grab this one down here again. What we're going to do is truncate this one, remembering this is a continuation number, and the next thing we need to do is head into the next character, B, and grab the remaining bits. So let's go ahead and do that. We have 000001. We can see the very first one is 0, which means it's not a continuation bit, so we have the remaining digits in here. Go ahead and truncate that one for now. And the next thing we need to do is concatenate these ones together. The first thing you might try and do is something like this and just concatenate them together. However, this would be incorrect. The reason this is incorrect, if we head back to the standard, we can see here it says the digits are encoded into the string least significant bit first. This is somewhat confusing, so just to give you an example with our usual number system, the decimal system, you have something like 201, which is 201. In this case, the most significant bit is first, so 2 is the most significant, then 0, then 1. What this is really saying is 2 times 100 plus 10 times 0 plus 1 times 1. And this is going to give you 201. And it is most significant bit first. If we were to rewrite this least significant bit first, it would be written like this, 102. This would still be valid as long as everyone knew it was least significant bit first and you had to read it backwards. A little bit unintuitive. It turns out this works out really well though for binary encoded values. So what this means is everything is going to be the opposite order. We have to grab this part and put it at the very end. I made a mistake there. Let's go ahead and try one more time. So this is going to be our final value. Now all we need to do is check for the sign. So the very last value is 0 in this case. We know it's going to be positive. I'm going to truncate that one and put the positive sign here. And if we did everything correctly, this is the final value. Let's go ahead and do our conversion just to make sure it is 0.000111001. That gives us 25. And that is exactly what I was expecting. So everything is now working correctly. It is a little bit confusing, but this is how it works. And that's all you need to know to be able to decode any of these values. And we're going to use this very large one as our last test case towards the end. Now that we've seen everything and how this all works, what we're going to do is actually start writing some code to see if we can automate this instead of doing this manually. So what I'm going to do is actually keep these ones here. They can be useful to have, but I am going to get rid of this REPL down here, make my screen slightly larger, and we're going to have a REPL on the side instead to keep track of everything. Just going to go ahead and run that in watch mode. We're going to use nodemon with TypeScript node as the runner, and then everything should be hopefully working correctly, and so it is. First thing I'm going to do is just go ahead and clear the screen to make everything a little bit more readable. And let's go ahead and create a new function in here. I'm going to call this one decode, and it's going to take a single argument for now. It's just going to be the string to decode. In this case, it is going to be a string. Let's just go ahead and return null just to make sure everything is actually working. And we'll go ahead and write our very first case. In this case, we're going to decode, let's say I, and we know that one is going to be 6, or was it 4? It's going to be 4. So if everything is working correctly, this should give us 4. Obviously, this is going to give us null for now. We haven't returned anything. So let's go ahead and actually return something. We're going to need some way to change this to Base64. And just to save a bit of time, I prepared something. It's just a very simple table. I'm just going to go ahead and grab this one over here and paste it in and delete these comments over here. All this is doing is creating a very little key value map, which is going to give me the correct number for any given character. So let's go ahead and try this one out. Just going to do a quick little console. In fact, I'm just going to return it in here. We're going to create a new value called int, and that's just going to be called a char to int. And we're going to pass in our character in here, which is going to be I in this particular case. Let's just go ahead and return it to see if it's working. If I save this off, we are getting 8, and that's exactly what we expected. We can go and double check that one here. We see I is indeed mapping to 8, which is exactly what we wanted it to do. Just a little bit of an aside, this can be very useful for debugging. You can do toString and pass in 2, and this is going to give you the binary representation. And you can see we are getting 1, 0, 0, 0 there, exactly what we expected. So the next thing we need to do is see if there's going to be a continuation bit. And the way we can do this is using a bitwise and I'm going to explain that one right now. So the first thing I'm going to do is create a new variable called hasContinuationBit. It's nice and descriptive. And what this is going to be equal to is int, and we're going to do a bitwise and on 32 in this particular case. This might seem a bit confusing, so let me show you how a bitwise and works. Our first value is going to be, in this case, 001000, and the second value is going to be 32, and 32, as we know, is bitwise in binary, is going to be 1, 0, 0, 0, 0, 0. And what this is going to do is tell us if the very final bit here is going to be a 1 or a 0, so whether it's a continuation bit. The way a bitwise AND works is it's going to return 1 if both the first and the column are both equal to 1. So in this case, we have 0 and 1. They're both not equal to 1, so it's going to be 0. And we have the same process again here, 0, 0, 0, 0, 0, 0. So this is always going to return 0 unless the trailing or the very first character is going to be a 1, in which case we would get 1. And that would indicate there is going to be a continuation bit. In this case, there's not, so we're going to get 0 here. So this is going to be a false value for this particular example. However, if there is a continuation bit, this will evaluate to true. The next thing we're going to do is consider that case. We aren't actually going to implement this right now. We're going to do that soon. And if this is not the case, in the case of I, we do not have a continuation bit, we are going to be able to continue on and figure out what to do next. So the next thing we were doing is what we did earlier. After we've seen if there's a continuation bit, we're going to go ahead and truncate that one. So I'm going to do that one here as well. I'm going to call this one without continuation bit for now. And we can truncate this with a nice little bitwise trick. We're going to end it with 31. The way this is going to work again, I'll just quickly show you. Something like this, and we're going to end it with 31, which we know is going to be 0, 1, 1, 1, 1, 1, 1. In this case, the first value here is always going to be 0. That means we're also always going to end up here by truncating that value. So this is going to evaluate to 0, 0, 1, 0, 0, 0. You can see here it's going to be the exact same value down here, but we are truncating that first value. In the case that this was having a trailing value or a leading value of 1, this would still become 0 because we're always passing in 0 here, because 31 in binary is always going to have that trailing or that leading 0. So this is effectively going to truncate that bit for us. The next thing we need to do is figure out if it is negative and return it. So at this point we have 001, 000. And the next thing we need to do is going to be down here. We're going to look at that very last bit here and see if it's 1 or a 0. There's a very easy way to do this again using bitwise operators. So we're going to have a new variable called neg, and that's just going to be equal without continuation bit here, and we're going to bitwise AND it with 1. Again, this is how it's going to work. It's going to be 0000001 in this case. So we're going to check here if this is going to be a 1 or a 0. If this is a 1, this is going to be a positive value, so it's going to be negative. We know it's negative. In this case, it's 0, so this is going to evaluate to something like this. And this is always going to be null in this case, or negative. It's not negative in this case because we have 0 up here on the first line and the 1 down here. So this is going to evaluate to 0, meaning this value is not negative. So therefore it is positive. If it was a negative value, we'd have 1 up here as well, and this would give us 1, so it would be true. So negative would be true. With this in mind, we can almost go ahead and return everything. The last thing we need to do is actually truncate that final value. We did say earlier if there was a final value of 1. So for example, in the particular case of, let's say this, we need to go ahead and truncate this one. The reason for this is this last value here, the sign is not part of the value. It's just indicating whether it's negative or positive. So we need to truncate that one somehow. There is a nice little trick to truncate this. What we can do is use a bitwise shift to the right. So what that does is going to take all of these values and move them 1 to the right, or 2 or 3, or however much we'd like to shift them. If we shift them by 1, it's going to end up doing something like this, and it's going to truncate the final value. So we're going to have this value here. We've effectively deleted this last character. Let's go ahead and see how we can do this. In this case, I'm just going to return without const bit here, and we're going to shift it to the right by 1. If everything's done correctly, this should actually work and give us the final value. Let's save it off, and then we'll explain how everything is working. You can see here I'm actually getting 4. So what we are doing here is we have this value at this point 1000. By shifting it bitwise to the right by 1, we're deleting this last trailing 0, and that's going to give us 4. If we shifted it again, we would be then getting an order of magnitude less, so we would get 2, and so on and so forth. So this is working just fine. We do need to consider the negative case, which we haven't done yet. Let's go ahead and see how this works without that first, and then update the code. So we said earlier that J was going to return -4, and if we save this off, we're still going to get, or 2 in this case, we should only be shifting by 1, so this is going to give us 4. We're not considering this negative value here. If we go ahead and do a console log on negative, we're going to see this is in fact a truthy value, which means the value is negative. So all we need to do is go ahead and add that in here. So if it is negative, we're going to just make this into a negative value. And if it's not negative, we're just going to do exactly the same thing, but we're going to shift it 1 again. Saving this off gives us the correct value of -4, and we can go ahead and validate this is working correctly as well. It is still giving us 4. The next thing I'd like to do before I can cover the more complex case of has continuation bits is going to be make this work with a number of characters. So for example, IIIM should give me a 4006 array. And the reason I want this is it's going to be very useful when it comes to creating this graph here, which we're going to use later on. So if I go ahead and save this one off now, it is not going to work. And the reason for that is we're passing in our full values into here, IAM, and that is not present in our dictionary up here. We only have the characters. What we need to do is grab the first character only in here. So I'm going to show you how we can do that. We're going to create a new destructor in here. So we're going to say ch and tail, and this is just going to grab the very first character, and the rest are going to be put into an array. We're just going to destructure that string in here. Just to show you how this works, I can go ahead and do a console log here of both ch and tail. And if we go ahead and update this one now, everything should be back to working, and we are getting 4. You can see here over on the right we have IAM, and the final characters are now become an array. That is what happens when you go ahead and destructure these. So what I'm going to do is put them back by saying const rest is equal to tail.join, and we're just going to join those ones up again. What this has done is accomplished something like this. And this is going to be very useful. Each time we iterate, we're going to go ahead and then truncate the very first one and continue on with the rest later on. Now that we've done that, let's go ahead and try and get the rest of the characters working as well. So what we're going to do is have to recurse to make this work. What this means we have to do is keep track of the decoded values in here. It is going to be an array of numbers, so let's go ahead and create that. Now what we need to do is see if we finished or not, and then if we haven't, we're going to push the new value into an array and continue recursing. For this reason, I'm going to create a brand new variable down here. I'm going to call it final val, and that's just going to be equal to the result of this down here. So let's actually go ahead and put it underneath. I'm going to grab all of this and put it in. So we're going to say final val is equal to this. If we go ahead now and return final val, we should still hopefully be getting something similar. And we are still getting 4. That is still working as expected. What we need to do now is actually go ahead, instead of returning final value, we need to keep on recursing for the rest of the values. So I'm just going to update this one down here. We're going to see if there's anything left. So if rest, if there is rest, we're going to continue recursing. Rest being the rest of these characters up here. So we're going to constantly make this smaller and smaller. If we have finished, however, we're just going to go ahead and return the characters. So we're going to say return decoded, being that array of decoded characters. Otherwise, what we're going to do is come in here and call decode again, passing in the rest of the values as well as the decoded values here. And we're also going to concatenate that with the most recently decoded value. So I'm going to say concat and pass in final val here. If we did everything correctly, we should be able to save this off and see everything working. We are getting an empty array, not really what I was expecting. This should actually be the opposite condition. And now we're getting 4, 0, 0. This is not quite what I was expecting, but we're pretty close. What we're going to need to do is figure out what we're missing. We are getting the first 3 characters, IAA. We are missing the M in here. So let's see if we can figure that one out. What we need to do is concatenate in here as well. So I'm going to concatenate that final value either way. Saving this off gives us the correct result, 4006. And this is getting a little bit closer to that goal we have over here to generate the correct mappings for each of the segments. So the next thing and the final thing we need to do is cover the more complex case of the continuation bits, whatever goes inside of here. So let's go ahead and set that one up. We have the example from before, which is YB, and we know if we do everything correctly, this should give us 25 in this particular case. If we save this one off now, it is not working at all. We get 9, negative 0. Clearly this is incorrect. What it's doing is taking each of these values individually, which is not what we want to be doing. We need to consider these to be a value together. And that's what we're going to do inside of here. Before we do that, we're going to make a slight update. So what we need to do is, if we have got this continuation bit, we need to consider that we're going an order of magnitude or 5 orders of magnitude greater. The reason it's going to be 5 orders of magnitude greater, as we said, is we're going to have 5 extra bits. So the first loop, if we go up to the top and remember our coding, it's going to have 110010. Sorry, 110010, and the next one's going to have 00001. And we are putting these together. We can't simply add these together because that would just be adding these 2 numbers together. What we need to do is correctly add these together, considering this is a fairly significantly larger number. This is going to be 5 orders of magnitude larger, so we're going to have to add on 5 trailing zeros. And this is going to represent the fact that it's the next significant bit. So we have to consider that has to happen as part of this process. So let's go ahead and update our code a little bit. What we are going to have to do is, considering this is recursive, we're going to have to make sure we consider all the previous numbers we've got as well and continue adding those up. So I'm going to create a new variable here called accumulator. It's going to start off as 0, and that's how we're going to keep track of it. We're also going to have depth. This is going to be number at 0 as well, and this is going to be the number of times we've recursed. Each time we recurse, we're going to increase this to know that we have to continually shift those bits over to get the correct magnitude. It's a little bit confusing, but let's go ahead and write the code and see how this is going to work. What we are going to do is create a new value in here. I'm going to call this one shifted, and what this is going to be equal to is without continuation bit, but we are going to shift this by 5 for each depth value we have in here. So we're going to shift it over by 5, and that's going to be to the number of depths. We're starting off with 0 depth, so this is always going to evaluate to 0. But then on the next iteration, this is going to be 5. So what this is going to do, given a value of, for example, 00001, it's actually going to shift this over by 5. So it's going to place 5 additional trailing zeros here. And this is indicating the fact that the second packet, it's going to be 5 extra bits larger than the previous one. Now that we've seen that, what we can do is create our new value in here, and that's going to be equal to the current accumulator, and we're going to add on that shifted value in here as well. And if we've done everything correctly, this value here is actually going to be exactly the same as what we need, regardless of the current loop. For the case of something like I, where it's a single value, this is always going to be evaluating to 0 over here. So this is always just going to be shifted here. It's just going to be equal to without constant bit, or without continuation bit, and that was what we were doing exactly before. What this does mean in practice is we can come down here and change this one here from without continuation bit just to be that value. And we can do the same thing here, and everything should still be working exactly the same. What we need to do finally is update our call signature, and everything should still be working the same way. We just need to change our values down here. What we're going to do, if we get to this point, it means there's no continuation bit we would have returned inside of here. So we're going to reset everything for the next digit. So it's just going to be 0 for both of these guys. Let's go ahead and actually test this out with our previous value, which was going to be IIIM. If we save this off, everything should be working the same, and it is still working the same. I know this is a bit of a mouthful here. What can be very useful is to go in here and do some console logs, and that's exactly what I'm going to do, just so we can track what is going on as we continue development. So far, we haven't got any additional shifting. This is always going to be 0, so these values are not changing at all. What we're now going to do is upgrade it for our final value, which is going to be the YB value. And all we need to do is create another call inside of here. It's going to be very similar to this decode call. I'm just going to bring it up here. But instead of having 0 for our depth and our accumulator, this is going to be the value, which should be value in here, which is going to be the sum of accumulator plus shifted, starting at 0. And this depth here is going to be depth plus 1, which is going to then give us the correct shift up here to get the correct magnitude. If we did everything correctly, this should actually be almost working. I'm just going to separate this out to make it a bit easier to read. And of course, we are going to have to change our return value for decoded here as well. We haven't finished decoding the value, so this is actually just going to be decoded. If we save this one off, we should hopefully have this working, and we are actually getting 25 there, which is exactly what we were expecting. You can see the value for shifted being logged twice. If we jump up to our original decoding here, we said the first time it was going to 110010. We have correctly truncated that continuation bit up here. That's working as expected. And you can see for the second iteration, we have this value here, which is 000001, which is just 1 in binary. Because we've added the extra 5 digits in here, we're actually getting that up here correctly as well. It's shifting it over by 5 digits. This does mean if we had another digit here, for example, maybe a Q or something like that, and this happened to have a continuation bit, we would then be shifting over by 10 digits and so on and so forth. Let's actually go ahead and see that one in action. We have this very large value here, 63C, which maps to 1405 if everything is done correctly. And if we paste that one in, save it off, we're going to see this is actually working. And you can see with our console log up here, we're actually shifting over twice at this point. So we have this value here, which has 5, and then another 5 following bits here, 1, 2, 3, 4, 5, and then we have 10 in here. So we've managed to shift that over correctly. And as things get larger, we're increasing the magnitude, which is exactly what we should be doing. So we've got everything working now. We have a ton of extra variables in here we probably don't need. We could make this more concise, but with bit shifting, things do get very confusing. So I'm happy to have everything be a little bit verbose if that makes it a little bit more readable and understandable. Before we move on to the next one, let's quickly review what we've done so far. So we saw a ton of interesting information here. We first saw the actual location for this specification and we read over it and understood what we were looking at. We learned about base64 values, how you can decode them. We then also saw a bunch of bitwise tricks. We saw the bitwise AND here. We saw the left shift here to shift the bits over to make it a larger number, in this case 5 orders of magnitude larger. And then finally down here we saw the opposite, which is the right shift. That's up here actually, where we actually were able to use it to truncate values on the end. So we saw a ton of interesting information here. There is another library that does this exact same thing called VLQ. You can go ahead and check that one out for an alternative implementation. It is a very similar implementation. It doesn't use recursion, which you might find a little bit easier to understand. And just to finally test this all out, I'm going to go ahead and add in a whole bunch of other values here. And this should give us what we expect, and that is the expected outcome there. So we've done a ton of work and we have this nice little decode function, and this is going to be very useful when it comes to decoding our maps, which we can see over here. We can go ahead and run it on this and find out all these values, and we'll be able to create our source map mappings. And that's going to lead us to the next lecture, where we're going to create a data structure to correctly represent this information here, which will then lead us to the final lecture, creating a nice little visualization like the one you can see here. I'll see you in the next lecture.